there is a number that should stop you cold. 13.8 billion years. That is how long scientists have told us the universe has existed. Born in a single, violent instant from nothing, expanding outward ever since, cooling, darkening, building the first atoms, then the first stars, then the galaxies we see today. That number, 13.8 billion years, is not just a figure in a textbook. It is the foundation of everything we think we know about existence itself, where we came from, why anything is here at all, what will eventually happen to it all. And for decades, that number held. Every telescope we pointed at the sky seemed to confirm it. Every measurement, every calculation, every peer-reviewed paper pointed to the same conclusion. The Big Bang happened, the clock started. The universe has been running for 13.8 billion years, and that is that. Then James Webb launched, and everything we thought we knew started to crack. Not slowly, not subtly. The cracks appeared almost immediately within the first months of Webb transmitting data back to Earth, and they were deep enough to make some of the world's most respected cosmologists say things they had never said before in public. Things like, "We do not understand what we are seeing." Things like, "These galaxies should not exist." Things like, "Our standard model of cosmology may be fundamentally incomplete." One astronomer, a man who has spent his entire career building the very framework that Webb appears to be shaking, used a single word to describe the early results. That word was monsters. He meant it literally. The galaxies Webb was finding in the earliest epochs of cosmic time were, by every measurement we had, impossible. This is not a story about a small discrepancy. This is not a story about scientists quibbling over decimal places. This is a story about the most powerful space telescope ever built, looking back to the very beginning of time and finding something that does not fit, something that, if confirmed, changes not just our understanding of galaxies and stars, but our understanding of the universe's entire origin story. This is the story of what James Webb actually found, what it means, why the scientific community is more divided about the Big Bang than it has been in 50 years, and why the answer to the question of whether the universe truly began the way we were taught might be stranger and more unsettling than anyone expected. Let's start where everything starts, with a decision made by one of humanity's most ambitious minds to look at the oldest light in existence, James Webb. Space telescope did not happen overnight. It was the product of more than 20 years of planning, design, construction, budget overruns, delays, political fights, and near cancellations. At one point, a congressional committee voted to kill the entire program. The project survived. It took somewhere in the neighborhood of $10 billion and the labor of thousands of engineers, scientists, and technicians across multiple countries to build a machine with a single overwhelming purpose: to see further back in time than any instrument ever built by human hands. To see, if possible, the very first light in the universe. Webb launched on Christmas Day, 2021. The rocket carried it out over the Atlantic Ocean, and for the next month the world watched with a mixture of hope and terror as it travelled 930,000 miles to its destination at the second Lagrange point, a gravitationally stable position where it would orbit the Sun in perfect lockstep with the Earth, always facing away from the warmth and light of our star, always looking outward into cold darkness. The telescope's golden mirror, 6.5 meters across and made of 18 hexagonal beryllium segments coated in a whisper-thin layer of gold, had to unfold in space, a process involving 344 individual single-point failures, any one of which could have ended the mission entirely. Every single one succeeded. By January of 2022, Webb was in position. By the summer of that same year, the first scientific images were released to the public, and in an instant, every previous image of deep space looked primitive by comparison. The images were breathtaking in a literal physical sense. Looking at the first Webb deep field, a patch of sky no larger than a grain of sand held at arm's length, you could see thousands of galaxies, not blurry smudges. Detailed, structured, impossibly clear images of galaxies in every shape. Spirals, ellipticals, rings, merging pairs twisted by gravity into strange and beautiful forms. Some of those galaxies were so far away that the light reaching Webb's mirror had been travelling for over 13 billion years. We were not just looking at distant objects. We were looking at the past, the early universe, the cosmic childhood. And that is when the trouble began. The Hubble Space Telescope, Webb's predecessor, could peer back to roughly 400 to 500 million years after the Big Bang. That boundary was not a hard wall, but beyond it things got too faint, too redshifted, too blurry for Hubble to resolve clearly. Webb was designed to push past that boundary, to see back to roughly 100 million years after the Big Bang, a time when the universe was still in its infancy, when the very first stars were just beginning to ignite in the primordial darkness. What scientists expected to find at those earliest epochs was predictably young things, small things, messy things. The universe, in those first hundreds of millions of years, should have been a chaotic place. Dense gas clouds, small and irregular proto-galaxies just beginning to coalesce, the raw ingredients of cosmic structure not yet fully assembled. That is what the standard model of cosmology, called lambda CDM, predicted. And lambda CDM had never been wrong, not in any significant way, not until Webb. What Webb actually found at those earliest epochs was not small, messy proto-galaxies. It found monsters. Enormous, fully formed, structurally mature galaxies. Galaxies that in some cases had already assembled a mass of stars comparable to or even exceeding our own Milky Way, sitting at redshifts above 10, meaning they existed less than 500 million years after the Big Bang. In February of 2023, a team of researchers led by Ivo Labbé published a paper in the journal Nature that sent shockwaves through the cosmological community. They had identified 6 candidate galaxies at redshifts between 7 and 10 that appeared to have stellar masses between 10 billion and 100 billion solar masses. Let that sink in. 100 billion solar masses. Our Milky Way contains roughly 100 billion stars. These galaxies, in some cases, had assembled a comparable amount of stellar material in less than 700 million years. Under everything we knew about how long it takes matter to collapse, form stars, and build galaxies, that timeline was not just tight. It was, by the calculations of multiple independent research groups, essentially impossible. Joel Primack, one of the architects of the lambda CDM model, the very framework that all of modern cosmology is built upon, read the Labbé paper and did not dismiss it. He called those galaxies monsters. He said, openly that the Standard Model did not predict anything like what Webb was finding. Mike Boylan-Colchin, a cosmologist at the University of Texas at Austin, published his own paper responding to the early Webb results. The title of the abstract contained a phrase that would have been unthinkable in cosmological literature 5 years earlier. He wrote that these galaxies were in serious tension with the current Standard Model of the universe, and that if the observations held up, our understanding of cosmic structure formation would need to be revised at a fundamental level. But here is where the story gets more complicated, because revised and wrong are very different words, and the history of science, particularly the history of cosmology, is full of moments where a crisis turned out to be not an overthrow, but a refinement. So before we go further, we need to understand exactly what the Big Bang Theory is, and what Webb's results do and do not challenge, because the popular narrative and the scientific reality are, as they so often are, not quite the same thing. The Big Bang is not a theory about an explosion in space. It is a theory about the expansion of space itself. The universe was not born inside some pre-existing void. There was no empty room into which matter exploded. Rather, the Big Bang describes the moment when all of space, time, matter and energy began to exist and simultaneously began to expand. The universe was not born in a point and grew outward. The entire fabric of space-time was born compressed, unimaginably hot and dense, and has been stretching in every direction ever since. This distinction matters because many of the alternative theories that Webb's results have emboldened, theories that claim the Big Bang never happened, are often conflating the actual scientific claim with a popularized misconception of it. But we will come to those theories shortly. The evidence for the Big Bang is not thin. It is not built on a single observation or a single experiment. It is convergent, meaning it comes from multiple completely independent lines of evidence that all point to the same conclusion. First, and most famously, the expansion of the universe itself. In 1929, Edwin Hubble discovered that virtually every galaxy we can observe is moving away from us, and that the further away it is, the faster it recedes. If you run that expansion backward in time, like a movie in reverse, everything converges to a single point, approximately 13.8 billion years ago. Second, the cosmic microwave background. In 1964, Arno Penzias and Robert Wilson accidentally discovered a faint, uniform glow of microwave radiation coming from every direction in the sky simultaneously. This radiation, now measured with extraordinary precision by satellites including COBE, WMAP, and Planck, is exactly what you would expect to find if the universe was once hot and dense and then expanded and cooled. It is the afterglow of the Big Bang itself, stretched to microwave wavelengths by 13+ billion years of cosmic expansion. Third, the abundances of light elements. Big Bang nucleosynthesis theory predicts that in the first 3 minutes after the Big Bang, the universe should have produced specific ratios of hydrogen, helium, and lithium. When astronomers measure the ratios of these elements in the oldest, most pristine regions of the universe, places untouched by later stellar nucleosynthesis, they find exactly what the Big Bang predicts, to remarkable precision. These 3 lines of evidence alone are robust enough that any alternative theory must account for all 3 simultaneously, and no alternative theory has ever successfully done so. So when Webb finds unexpectedly massive early galaxies, it does not disprove the Big Bang. The universe was clearly hot and dense in its infancy. The cosmic microwave background tells us that with overwhelming certainty. What it challenges is a more specific set of claims about how quickly structure forms after the Big Bang, how fast matter clumps together under gravity, how efficiently gas collapses into stars, how long it takes to build a galaxy the size of the Milky Way. These are not claims about the Big Bang's validity. They are claims about the physics of galaxy formation and the role of dark matter in the early universe. And they are the claims that Webb is tearing apart. Here is why these massive early galaxies are such a problem. According to lambda CDM, the lambda here refers to dark energy, the CDM to cold dark matter. The universe builds structure hierarchically. Small things form first. Tiny fluctuations in the density of matter from the very earliest moments of the universe gradually grow under the influence of gravity. Dark matter, which does not interact with light, and therefore begins clumping much sooner than ordinary matter, forms a cosmic scaffolding, an invisible web of filaments and halos into which ordinary matter eventually falls. Gas accumulates, cools, collapses further under its own gravity, and eventually the density and pressure become high enough to ignite nuclear fusion. Stars are born. Many generations of stars live and die. Heavier elements are forged in their cores and scattered by supernova explosions. Gradually, star clusters merge into dwarf galaxies, which merge into larger galaxies, which merge again and again over billions of years into the massive structures we see today. This hierarchical assembly process takes time. A lot of time. The simulations built on lambda CDM predict that building a galaxy with the stellar mass of the Milky Way should take somewhere between 2 and 4 billion years at minimum. Possibly longer. The very first stars, population 3 stars, the mythical, unobserved giants of the early cosmos, formed entirely from hydrogen and helium because no heavier elements existed yet, are not predicted to appear until roughly 100 to 200 million years after the Big Bang. The first small proto-galaxies form a few 100 million years in. But massive, fully assembled galaxies, billions of solar masses in size, those take time. Billions of years of mergers and star formation. The simulations say so. The models say so. Everything says so. Except Webb. When Labbé's team found those 6 candidate galaxies, when they measured their redshifts and calculated their stellar masses, they were not just seeing galaxies that were older than expected. They were seeing galaxies that, under any standard cosmological framework, could not have had enough time to form. One of the 6 candidates was estimated to have a stellar mass of roughly 100 billion solar masses, at a redshift of approximately 7.4, corresponding to an age of the universe of roughly 700 million years. In the standard model, at 700 million years, the universe should not yet have had the resources, the time, or the physical mechanisms to build something that enormous. The numbers simply do not work. You cannot form that many stars in that amount of time, given the rates of star formation that the models allow for. it is like being told that a human embryo, at 5 days of development, already has a full set of adult teeth. It contradicts everything we know about the timeline of development. But here is the first twist, the first drop in the roller coaster, because science never gives you a clean narrative. Within months of the Labbé paper, skeptics began to push back, not because the observations were wrong, but because interpreting distant galaxy data is extraordinarily difficult. The masses of those early galaxies were estimated using photometric methods, essentially measuring the brightness of the galaxies in different wavelengths of light, and using those brightness profiles to infer how much stellar mass must be there. But those inferences depend on models of stellar populations, assumptions about dust, and assumptions about the star formation history of the galaxy. And those assumptions can be wrong. Some researchers argued that what appeared to be massive old stellar populations might in fact be dominated by a relatively small number of extremely bright young stars, so-called bursty star formation, in which galaxies go through intense periods of rapid star formation that temporarily make them appear much more massive than they actually are. If that were the case, the crisis might be less severe. For a brief, hopeful moment, it seemed like the monsters might be an illusion, a measurement artifact, a reminder that cosmology is hard and that initial results must always be treated with caution. And then Webb kept looking. More data came in. Spectroscopic follow-up observations, the gold standard of extragalactic astronomy, because spectroscopy measures the actual light signatures of individual elements in a galaxy's stars, giving you a much more reliable picture of the galaxy's age and composition, began confirming that yes, many of these early galaxies were genuinely, stubbornly massive. They were not illusions produced by bursty star formation. They were real. The tension did not evaporate with more data. It deepened. By 2023 and into 2024, the evidence had accumulated to the point where mainstream cosmology could no longer wave it away. A landmark paper by Michael Boylan Colchin in Nature Astronomy quantified the problem with brutal precision. He showed that even in the most optimistic scenarios, even if you assumed the maximum possible efficiency of converting gas into stars, even if you pushed every free parameter in the models to their most galaxy-friendly values, the lambda CDM model still could not produce galaxies as massive as the ones Webb was finding at those redshifts. The impossible galaxies were not a quirk of one dataset or one team's analysis. They were a systematic pattern appearing across multiple independent surveys and multiple research groups. The crisis was real. Now we arrive at the part of the story where things get genuinely strange, where the roller coaster climbs to a new height and you can see much further than you expected. Because while mainstream cosmologists scramble to find ways to patch the lambda CDM model, adjusting dark matter models, invoking new physics, questioning whether dark energy behaves differently in the early universe, a different set of voices began to grow louder. Voices that had been saying for decades at the margins of cosmological discourse that the Big Bang model was fundamentally broken. And those voices now had something they had never had before, a major telescope appearing to support their claims. Chief among them was Eric Lerner, a plasma physicist and science writer who for over 30 years has argued in favor of an alternative cosmological model based on plasma physics rather than the Big Bang. In the immediate aftermath of the early Webb results, Lerner wrote a widely shared article with a provocative title, arguing that Webb was confirming what he had predicted all along, that the universe does not have a beginning, that it is not expanding in the way the Big Bang model claims, and that the apparent redshift of distant galaxies can be explained by mechanisms other than Doppler recession. His article spread rapidly across the Internet, was picked up by popular science outlets, and sparked a wave of public discussion about whether the Big Bang was actually on its last legs. But here is where honesty becomes essential, because this story, like all the best stories, demands it. Eric Lerner's plasma cosmology model does not actually account for the cosmic microwave background. It cannot explain the precise ratios of hydrogen and helium that Big Bang nucleosynthesis correctly predicts. It doesn't reproduce the large-scale structure of the universe, the cosmic web of filaments and voids, that simulations based on lambda CDM match with extraordinary accuracy. Lerner's model has been in circulation for decades and has repeatedly failed to pass the quantitative tests that a physical theory must pass to be taken seriously. The scientists who published the early Webb results were, almost to a person, clear and explicit about this. Their findings challenged galaxy formation models, not the Big Bang itself. Lerner's interpretation, they said, was not supported by the data. And yet, and this is the crucial point, the place where intellectual honesty demands we sit with discomfort. The fact that Lerner is wrong does not mean that everything is fine, because the problem Webb revealed is not small. It is not a footnote, and the cosmological community knows it. Let us talk about dark matter for a moment, because it sits at the center of this crisis in a way that is rarely discussed in popular accounts. The lambda CDM model requires dark matter, a form of matter that does not emit, absorb, or reflect light, but does interact gravitationally to be the scaffolding on which all cosmic structure is built. Without dark matter, there is no reasonable way to explain how ordinary matter clumped together fast enough to form the galaxies and galaxy clusters we observe. The cosmic microwave background has acoustic oscillations, tiny ripples in its temperature, that can only be explained if most of the matter in the early universe was a non-electromagnetic, gravitationally clustering fluid. That is dark matter, and the CMB's acoustic peaks match the dark matter prediction to extraordinary precision. Dark matter is real. We have never detected a dark matter particle directly in a laboratory, but the gravitational evidence for its existence is overwhelming. Here is the problem. The simulations that told us how quickly galaxies form assume a specific type of dark matter, called cold dark matter. Cold, meaning it moves slowly compared to the speed of light in the early universe. Cold dark matter forms halos efficiently, clumps on small scales first, and drives that hierarchical bottom-up galaxy formation process we described. But if those simulations are producing galaxies that are too small and too few in the early universe compared to what Webb is finding, there are two possible explanations. Either something is wrong with our models of how gas converts into stars. The efficiency of star formation is higher than we thought. Or something is wrong with dark matter itself. Not wrong as in dark matter doesn't exist, but wrong as in cold dark matter might not be the right description. Some theorists have been advocating for years for what they call warm dark matter, particles that move faster and therefore resist clumping on small scales while still producing large-scale structure. Others have proposed fuzzy dark matter, axion dark matter, or self-interacting dark matter, each with different behaviors on cosmological scales. The Webb results have breathed new life into all of these alternative dark matter models, because any model that causes dark matter to clump more efficiently in the early universe, or that allows star formation to proceed more efficiently, could, in principle, produce the massive early galaxies Webb is finding without requiring us to throw out the Big Bang. But there is another possibility, one that is harder to swallow, more radical in its implications, and that has gained serious traction in the cosmological community as Webb data has accumulated. The possibility that dark energy, the mysterious force that is causing the universe to accelerate in its expansion, represented by the lambda in lambda CDM, does not behave the way we assumed. Einstein introduced the cosmological constant, his greatest blunder, as a mathematical term to keep the universe static. When the universe turned out to be expanding and then accelerating, it was reinstated as a description of dark energy, a constant energy density pervading empty space, causing the expansion to accelerate at a fixed rate. But what if dark energy is not constant? What if it changes over time? In 2024, a major new analysis of data from the Dark Energy Spectroscopic Instrument, or DESI, measuring the large-scale structure of the universe across 11 billion years, found preliminary evidence that dark energy may indeed be evolving, getting weaker over time. If dark energy was stronger in the past, it would have affected the rate of expansion in the early universe, which in turn would have affected when and how dark matter halos formed, which would have affected galaxy formation. The implications cascade through the entire model. A universe with evolving dark energy is not the universe that lambda CDM describes. It is something more complex, more dynamic, something that we do not yet have the mathematical tools to fully model. And a universe with evolving dark energy is a universe where the formation of early massive galaxies might be less surprising than the current standard model predicts. All of this brings us to the Hubble tension, a problem that predates Webb, but that Webb has made significantly more urgent. The Hubble constant, named after Edwin Hubble, measures the rate at which the universe is currently expanding. It is arguably the single most important number in cosmology, because it determines the age of the universe, the size of the observable universe, and the entire timeline of cosmic history. For decades, there were two competing methods of measuring it. The first, the early universe method, uses the cosmic microwave background to infer the expansion rate by projecting forward from the Big Bang. The second, the late universe method, measures the distances to and recession velocities of galaxies directly, using standard candles like Cepheid variable stars and Type 1a supernovae. These two methods should give the same answer. They do not. The early universe method gives a value of approximately 67 kilometers per second per megaparsec. The late universe method gives approximately 73. That difference, known as the Hubble tension, is now significant enough, roughly 5 sigma, meaning it has less than a 1 in a million chance of being a statistical fluke, that it cannot be explained away as measurement error. Something is physically wrong. Either one of the measurements is systematically biased in a way that no one has yet identified, or the universe behaves differently in its early phases than in its later phases, in a way that our models do not currently account for. Webb has made the Hubble tension more acute by providing the most precise measurements yet of Cepheid variable distances, strengthening the late universe measurement and making it harder to argue that observational error is responsible for the discrepancy. The tension is real. It points to new physics, physics beyond the standard cosmological model. And when you put the Hubble tension together with the problem of the massive early galaxies, what you begin to see is a picture of a cosmological model that works extraordinarily well over most of cosmic history, but that shows signs of strain at its boundaries, in the very early universe and in the most precise measurements of the present-day expansion rate. So where does that leave the Big Bang? Let us be absolutely precise about this, because the answer matters. The Big Bang, the event itself, the idea that the universe began in a state of extreme heat and density and has been expanding and cooling ever since, is not in serious jeopardy. The cosmic microwave background, with its extraordinary precision and its match to theoretical predictions, is a near-definitive fingerprint of a hot, dense early universe. Big Bang nucleosynthesis, with its precise predictions of elemental abundances that match observations to within a few %, is strong independent corroboration. The large-scale structure of the universe, the way galaxies cluster into filaments and walls separated by vast voids, matches the predictions of a universe seeded by quantum fluctuations in the earliest moments of inflation, expanded and structured by dark matter over billions of years. These agreements are not coincidences. They are the product of a physical model that captures something genuinely true about the universe. What is in serious jeopardy, or at minimum in serious need of revision, is not the Big Bang, but the specific framework of lambda CDM and its predictions about how structure forms in the early universe. This distinction might seem like academic hair-splitting. It is not. The difference between the Big Bang never happened and our model of post-Big Bang galaxy formation needs revision is the difference between a revolution and an evolution. Revolutions in science are rare. Evolutions are constant. The history of cosmology is littered with models that needed revision without the underlying framework being overturned. Newtonian gravity needed revision. It became general relativity. Classical thermodynamics needed revision. It became quantum statistical mechanics. In each case, the revision was not a repudiation of the preceding framework, but a deepening and extension of it. The most likely outcome of the Webb crisis, if we are being honest, is not the death of the Big Bang, but a significant reconfiguration of our understanding of dark matter, dark energy, and the efficiency of early star formation. Perhaps we need warm or fuzzy dark matter instead of cold dark matter. Perhaps star formation in the early universe was far more efficient than we modelled, driven by different mechanisms: magnetic fields, turbulence, the absence of heavy element pollution, that slows star formation in later epochs. Perhaps dark energy is indeed dynamic rather than constant, and the universe's expansion history is more complex than a simple cosmological constant allows. Perhaps all three of these things are true simultaneously. But, and this is the twist that keeps appearing, the high in the roller coaster that follows the drop, there is one scenario that even mainstream cosmologists are now forced to take seriously, one that would have seemed outrageous a decade ago. The scenario where the early universe had a phase of structure formation that was fundamentally different in character from what came after. A universe that did not build itself from the bottom up in a smooth, hierarchical progression, but that instead, perhaps due to some physics that we do not yet understand, perhaps related to the inflationary epoch, perhaps to some exotic behavior of dark matter at high densities, experienced bursts of rapid, massive structure formation in its first billion years that left behind the galaxy monsters Webb is now finding. A universe with a more dramatic, more violent, more surprising early history than any of our models predicted. This scenario does not disprove the Big Bang, but it does suggest that the Big Bang seeded a universe far stranger and far more complex than we imagined. A universe that in its infancy did not develop gradually and predictably, but leaped in some regions, at some times, into structures of staggering scale and maturity at speeds that defy our current physics. And if that is true, then the question is not whether the Big Bang happened. The question is what the Big Bang set into motion, and whether our equations are anywhere near adequate to describe it. Here is one more fact that deserves its own moment of silence. In 2022, using data from the James Webb Space Telescope, astronomers confirmed the detection of carbon dioxide in the atmosphere of a planet called WASP 39b, a gas giant orbiting a star 650 light-years away. This was the first direct detection of carbon dioxide in an exoplanet atmosphere in history. One telescope, one observation, and it changed the field of atmospheric characterization forever. That same telescope, that same gold-mirrored, sun-shielded, Lagrange-parked marvel of human engineering, is now looking at planets closer to Earth's size and closer to the habitable zones of their stars. It is measuring the chemical compositions of atmospheres on worlds that might, just might, harbour something extraordinary. But we are getting ahead of ourselves, because Webb is not finished with the early universe yet. The surveys are ongoing, the data is still flowing in, new papers appear every week, and with each new paper the picture becomes simultaneously clearer and more baffling. Clearer because the instruments work flawlessly, and the data quality is extraordinary. More baffling because the universe, as always, refuses to conform to the neat story we had written for it. Stéphane Charlotte and colleagues have been using Webb to study the epoch of rionization, the period between roughly 150 million years and 1 billion years after the Big Bang, when the first stars and galaxies produced enough ultraviolet light to ionize the neutral hydrogen that had filled the universe since the cosmic dark ages. Webb is mapping this epoch in detail for the first time, and what it is finding there challenges models of early galaxy feedback. The way energetic output from massive stars and black holes shapes the surrounding gas. The ionizing photon budgets do not add up the way they should. There are more ionizing photons in the early universe than the models predict, which means there are either more early galaxies than we thought, or those early galaxies were producing radiation far more efficiently than any present-day galaxy does. Again, not a repudiation of the Big Bang, but another piece of a growing mosaic that says our second-tier models, the models that describe what happens after the Big Bang creates the initial conditions, need to be rebuilt from the ground up. And then there is the question of the first black holes. Webb has detected supermassive black holes, objects containing billions of solar masses of compacted matter, at redshifts above 6, meaning they existed less than 1 billion years after the Big Bang. Supermassive black holes are found at the centers of virtually every large galaxy in the observable universe, including our own Milky Way, which harbors one called Sagittarius A star, with a mass of approximately 4 million solar masses. But how you build a black hole containing billions of solar masses in less than 1 billion years is, under standard accretion physics, deeply problematic. Black holes grow by consuming surrounding matter, and that process has a natural speed limit called the Eddington limit, above which radiation pressure from the infalling material blows away the gas before it can be swallowed. Growing a black hole of 1 billion solar masses from a stellar remnant seed of perhaps 100 solar masses in less than 1 billion years requires sustained Eddington-limited accretion for almost the entire period, with essentially no pauses. The statistics of that kind of sustained growth are vanishingly small. Again, possible but improbable, unless the seeds were bigger to begin with. Unless the first black holes did not form from stellar remnants, but from the direct collapse of massive gas clouds in the early universe, an exotic formation channel called direct collapse black holes, that some theorists have advocated for years, but that had almost no observational support until Webb began finding these extreme early quasars. Every one of these puzzles is individually potentially explainable within a modified version of the standard model. Taken together, they paint a picture of an early universe that was more active, more structured, more efficient at building massive things than any of our models predicted. And the intellectual honesty that science demands requires us to say clearly, we do not yet know why. We do not know whether the answer requires new dark matter physics, new dark energy physics, new black hole formation channels, new star formation mechanisms, or some combination of all of the above. We do not know whether the answer is inside the current framework or outside it. What we do know is this. The James Webb Space Telescope was built to answer questions. Instead, in the finest tradition of every great scientific instrument before it, it has generated new ones, better ones, deeper ones. The Hubble Space Telescope, when it was first turned on, had blurry mirrors that made everything look smeared and uncertain. Engineers fixed it, and it went on to transform our understanding of the universe's age and expansion history. Webb's mirrors are perfect. Its instruments are working exactly as designed. The uncertainty it has introduced is not a problem with the telescope. It is a problem with us, with the limitations of the models human beings have built to describe a universe of almost incomprehensible size and complexity. That is not a failure. It is science doing what science is supposed to do. finding the places where our understanding ends and the genuine mystery begins. The Big Bang happened. 13.8 billion years ago, the universe was born hot and dense and has been expanding ever since. That part of the story is not going anywhere. But what happened in those first billion years, how matter assembled into the first stars, the first black holes, the first galaxies, that story is being rewritten. By Webb. Right now. In real time. With data so precise and so unexpected that even the people who built the telescope did not see it coming. And here is the final note. The one that should sit with you longest. When scientists say that the early galaxies Webb found are impossible, they do not mean that they cannot exist. They exist. Webb photographed them. They mean that within the current framework there is no explanation for them, which means the framework needs to change. And frameworks changing is how science advances. It is not a crisis, it is a gift. Because every time the universe refuses to conform to our expectations, it is telling us something true about itself, something we did not know before, something that takes us one step closer to actually understanding what this place is. This cosmos that began in fire and silence, that built galaxies and stars and planets, and on at least one of those planets built creatures who look up and ask where they came from. Webb is our best answer yet to that question. And the answer it is giving us is more honest, more surprising, and more beautiful than anything we expected. The universe is older in some places than our models allow. The first structures formed faster than physics should permit. The darkness between the galaxies is not empty but full of forces we cannot see and have barely begun to measure. 13.8 billion years. The clock started. And we are only now, with the most powerful eyes humanity has ever built, beginning to read what a time actually wrote.